This video is kind of a short one, and I don't really have a title that I want to give to it. I'm just going to kind of say a little bit like it's really more of an odds and ends kind of video. These are some things that are important and that you need to know and that you need to be able to do for chemical equilibria. But I'm not really going to give a specific title to them. So let's say, for example, in the first case that we're going to discuss, we've got these two reactions right here. So A plus B is in equilibrium with the product C and D, and C and D are in the equilibrium with the products E and F. These two equilibrium, as they are expressed, are, as you can see, dependent upon each other. So we might consider, let's say, this reaction and this reaction to be the steps involved in a final reaction, which is going to look like, hang on one second, I don't know why it continues to do that, but it does, which will kind of look like this as we go forward. So these two might represent steps that occur in order to form this final equation, which represents the reaction that we are of interest in. So maybe A plus B form these intermediates C and D, and then the intermediates C and D react to form E and F. And of course the two intermediates cancel each other out, and you won't find them in the overall reaction. And so this overall reaction really consists of these two equilibrium steps. Now we can write a K sub C for this equation, and we'll call it K sub C prime. And we can write a K sub C for this equation, and it's K sub C double prime. So K sub C prime is equal to the concentration of C times the concentration of D over the concentration of A times the concentration of B. And again, these are all at equilibrium. And of course our K sub C prime is equal to the K sub C, double prime is equal to E, the concentration of E times the concentration of F divided by the concentration of C times the concentration of D, and again all at equilibrium. Well, the question becomes, how do we find the K sub C for the overall reaction? Well, like Hess's law, where we've seen in the past that we might be able to take the delta H's and add the two delta H's up to get the delta H of the final reaction, we see that it's not really possible to do that with K sub C's. If we took these two and added them up, we would not get the K sub C for this reaction. The K sub C for this reaction being equal to the concentration of E times the concentration of F divided by the concentration of A times the concentration of B. So remember, it's products concentrations over reactant concentrations. So how does this relate to these two right here? Well, again, if we try to add them up, we wouldn't get this. But we do notice that C and D are on top here and they're on the bottom over here. And if we can get them to cancel, we would be left with E and F on the top, like we have in our overall equation. And we'd have A and B left at the bottom, like we do in our overall equation. So in order for that to occur, we would have to take those two and multiply them. So it turns out that K sub C for the overall reaction is equal to K sub C prime times K sub C double prime. So if we know the K sub C expressions or values for the two reactions or three reactions or 10 reactions, how many there are, that actually are the steps involved in the final reaction, we could just take those K sub C's and multiply them out, and we'd see that the C would cancel with the C, the D would cancel with this D, we'd be left with E and F on top, A and B on the bottom, and we would get the K sub C for the overall reaction. So if a reaction can be expressed as the sum of two or more reactions, the equilibrium constant for the overall reaction is given by the product of the equilibrium constants of the individual reactions. And that is an important and interesting, let's call odd or end, to this particular question, or not to this particular question, but this particular topic. So take a minute, write down whatever you need to write down. stop the video, and then move on. Now, here we have a particular reaction. N2O4 gas in equilibrium with 2NO2 gas. And what we're going to try to show you with this particular slide is that the value of K and the expression of K, the K sub C or the K sub P, whichever, is dependent upon how you write the particular reaction. So we can see if it's written this way, N2O4 on the left and NO2 on the right, the expression is the NO2 concentration raised to the coefficient, so it's NO2 squared, divided by the N2O4 concentration. And again, these are equilibrium concentrations. Ends up being equal to the value 4.63 times 10 to the negative third. Well, let's take the equation and turn it the other way. Let's take the NO2, which was on this side, and place it over here, and take the N2O4, which was on this side, and place it over there. So you see, we've kind of taken the products and the reactants, which we normally call product and reactant, and kind of switch sides, which we can do because it doesn't really matter, because this is an equilibrium. And remember, if it's an equilibrium, the forward reaction is taking place, but the reverse reaction is also taking place, and you really can't single out one thing as being the reactant and the other thing as being the product. Technically, they're both reactants and they're both products. So we can take that equation, we can write it in the opposite way, and when we do, the K looks like this. So now we've got N2O4 concentration as the product and the NO2 concentration squared as the reactant. And when we do that, it turns out that this K sub prime here, the K for this reaction as it's written, is just the reciprocal or the inverse of the K for the previous reaction, which is basically the same reaction, only what is written on the right is now written on the left, and what's on the left is now written on the right. So if you take an equation, right, and you know the K expression and the value of K, if you take that equation and flip it so that what was on the left is now on the right and what was on the right is now on the left, the K for this new equation that you have now produced by flipping the previous one is just the reciprocal or 1 over K for this reaction here. And that's important to know. And it ends up being 216. So the value of K and the expression for K is dependent upon how you write the equation. And that says that right here. It says when the equation for a reversible reaction is written in the opposite direction, the equilibrium constant becomes the reciprocal of the original equilibrium constant. So take a minute, stop the video, write down what you need to write down, and then move on. Writing equilibrium constant expressions. The concentration of the reacting species in the condensed phase are expressed in moles per liter. In the gaseous phase, the concentrations are expressed in moles per liter, or in terms of pressure atmospheres. The concentrations of pure solids, pure liquids, and solvents do not appear in the equilibrium constant expressions. The equilibrium constant is dimensionless quantity. In quoting a value of the equilibrium constant, you must specify the balanced equation and the temperature. Why? Because the equilibrium constant can change depending upon how the equation is balanced and the temperature. And last but not least, if a reaction can be expressed as a sum of two or more reactions, the equilibrium constant for the overall reaction is given by the product of the equilibrium constants of the individual reactants. Now, there's one more thing that I want to discuss with you, although you won't see a slide on it here. There's one more thing I want to discuss with you about the equilibrium constant and the expression for the equilibrium constant, and how one more thing can affect it. So we saw that flipping it can affect it. In other words, flipping the equation so that now what was on the right is on the left, and what's on the left is on the right. But also another thing that affects it is if we multiply the equation times a number. And so in class, when we get together tomorrow, I'm going to talk to you about how multiplying the equation by a number affects the value of K and the expression for K. So that's it for now. Have a good night, and we'll talk to you tomorrow.